This video, we're going to continue what we did last time with centroids, but instead of finding them using integration, we're going to be looking at finding the centroid of what we call composite shapes, or shapes that are built up of simple shapes. So more centroids today, but no integrals, because it turns out most of the things that we build and work with as engineers are quite simple shapes. We might have an I-beam. Well, an I-beam, you don't need to integrate anything to find the centroid of an I-beam. You simply need to know the centroids of those three rectangles that it's made up of, and then combine them using a fairly simple formula. So we're going to say today we're doing centroids of composite shapes. So we could have I-beams, we could have T-shaped beams, we could have a half circle with a half circular hole out of it. Any of these kind of shapes are really made up of basic geometric shapes. So this is going to be kind of a table lookup sort of a day-to-day. We're going to be dealing with rectangles, triangles, circles, half circles, those kind of shapes. And in the back of the book is a table of centroids. And some of these you automatically know, right? I think you know that the centroid of a rectangle is right in the middle of that rectangle. Some of the other shapes, like a half circle, you probably would need to look up. So the formula we're going to use to find centroids here is to find the x-coordinate of a centroid. What we did before is we did an integral of x dA over the total area, integral of dA. Well, now instead of dealing with little tiny differential elements where we need to integrate, we're going to convert this into just a simple sum because we have a discrete number of parts. For the I-beam, we have three rectangles. So we're simply going to sum up the x-centroid location of each rectangle times the area of each rectangle. And then on the bottom, we will simply sum up the area of those rectangles. And we sum over how many shapes we have. We simply need to find the area of each shape and the centroid location of each shape. In the y direction, the equation is going to be summation of y tilde times area divided by the total area. So let's do a really quick example. My first example just has two shapes, an L-shaped cross section. And we are told that the x-axis is along the bottom, the y-axis on the left edge, and we are asked to find the centroid location. As we find the centroid location, we typically call that the x prime axis and the y prime axis. But what we're looking for is how far is that centroid from the origin. So we're ultimately looking for an x coordinate of the centroid, x bar, and the y coordinate of the centroid, y bar. And I do need some dimensions for my shape. The overall shape is 6 inches tall. And the smaller box on the side is 2 inches tall, and the total width is actually 8 inches, but it's broken up into a 2-inch piece followed by a 6-inch piece. So we just have two rectangles that are both 6 inches by 2 inches that are joined together, and we're going to use that information to find the centroid of the entire thing. I'm just going to, so it doesn't get too messy, I'm going to draw my shape again over here. And I do like to draw out how I'm breaking it up. I'm going to break it into a vertical rectangle that's 2 by 6 and a horizontal one that's also 2 by 6. I'm going to call this shape 1, call this shape 2, and I will need to find the centroid location of those two shapes measured relative to my original origin, which is right back there. And that is super important that you measure all of those centroid distances back to the original origin. I like to kind of color code these two, partly because colors make it fun. We'll make this one the pink rectangle, and we'll make this one down here the blue rectangle. We're assigned to find x bar and y bar, the coordinate location of the centroid, both the x and the y coordinate. So that's what we're trying to find. There are a couple of ways to do this. I'm first going to show you the table way, which I think a lot of you will like. So the idea with the table is I'm going to start, make a nice big table, and I'm going to tabulate things for area 1, for area 2, and then for some of these columns, I'm going to sum everything up and have a row for where I sum things. So the first thing we're going to need, we're going to be doing sums with all of these things on them. We're going to be summing areas. So we need to find the area of each shape. We also need to find x coordinate and y coordinates of each of those centroids. So let's start with the area. And the area of my pink shape, rectangle number 1, is going to be 6 inches times 2 inches, which is equal to 12 inches squared. And the other rectangle is also a 6-inch times 2-inch rectangle. So that's 12 inches squared. And this, I can add these two up. So my total area will be 24 inches squared. I also need to find the x coordinates of the centroids for each of the rectangles. So for my pink rectangle, the whole thing it's 2 inches wide. So my centroid would be 1 inch over. Call that 1 inch. And for my blue rectangle, the whole blue rectangle is 6 inches wide. Half of that would be 3, so I need to come over here 3 inches, but now I need to measure that centroid location all the way back to the origin. So I'm going to write this x tilde down as 5 inches. Let's make a column for x tilde times the area. So 12 square inches times 1 inch is 12 inches cubed. 12 square inches times 5 inches is 60 inches cubed. And I can sum those and I'll get 72 cubic inches. And now I'm ready to calculate x bar if we want. X bar is the summation of the x tildes times their individual areas over the summation of all the areas, which is 72 inches cubed divided by 24 inches squared. And that comes out to be a nice round 3 inches. We should have an upper and lower bound on what this should be to give us a quick sanity check of whether this number makes any sense. So my whole shape was 8 inches wide. So I'm expecting a number between 0 and 8. And I would expect that since I've got more area on the left than I do on the right, that rather than between 0 and 8, it's not going to come out right at 4. It's going to come a little bit left of that. The 3 inches is a little bit left of center for the overall shape. Another check is if one of your centroids is at 1 inch and the other one is at 5 inches, your overall centroid has to be somewhere in between the two of those. So same process for the y direction. There's y tilde. For my pink box, the whole rectangle is 6 inches high. Write it down. The whole thing is 6 inches high. So half of that will be 3 inches. So 3 inches is my y tilde location for that first box. And then for the other one, it's 2 inches high. And so the centroid would be half of that, 1 inch up, and I'm measured right relative to the origin. So I just write that down as 1 inch. Now multiplying y tilde times areas, I have 12 square inches times 3 inches, which is 36 inches cubed, and 12 square inches times 1, which is 12 inches cubed. I add those and I get 48 inches cubed. So for my y bar, it's just the sum of the y tildes times area over the sum of the areas, which is 48 cubic inches divided by 24 square inches. And I think that comes out to be exactly 2 inches. So my x bar was at 3 inches, y bar is at 2 inches. And again, looking at kind of a sanity check here, since one of my centroids was 1 inch up, the other one was 3 inches up, it makes a whole lot of sense that the actual total centroid would be in between the two. And since the two areas are the exact same size, the weighted average comes out to be exactly at the 2 inch mark. So that's using tables. Another way to do this would be to just write it in line. I'm summing up x tildes times areas. And if you're a shortcut person and don't want to write out that table, you can try this out. So I'm going to have a division when I'm done. On the bottom, I need the area of each of them. So the first area is 6 inches times 2 inches. On the top, I'll have something times 6 inches times 2 inches. So just filling in the areas of my pink rectangle. I will also have added to those for my blue rectangle an area of also 6 inches times 2 inches. On the top, I'd have another area. Oh, I need to leave a space. Area of 6 inches times 2 inches. And then I need to multiply each of those on the top by the x coordinates of their centroids. And we already figured these numbers out, but the first one will be 1 over. So I multiply this one times 1 inch. And then the other one is 2 plus 3, so 5 inches over. And then you simply do the math and you get the exact same answer. This comes out to be 72 cubic inches divided by 24 inches squared, which is 3 inches. And I don't know that this is any faster. It's definitely less writing. However, then you're doing these calculations multiple times as opposed to calculating it once and then using it here and here and here on the bottom one time. You're actually having to do calculations multiple times. The important thing to mention, though, is that all of our distances, all the x tilde and y tilde distances must be measured from the origin. That is the mistake that students make over and over. The mistake that I would see students make in here would be with this number right here. A lot of students will just drop in 3 inches because the rectangle is 6 inches wide, and so they drop it in as 3 inches. And it's not, it is 3 inches from the edge of the rectangle, but we need to measure it all the way back to the origin. This is not the only way to solve this problem. If you wanted to, you could, there are 2 other ways that would make a whole lot of sense to solve the problem. One would be to divide it into a horizontal rectangle that is 2 by 8 and a vertical rectangle that's 2 by 4. You should get the exact same answer. Another way that's not too bad to solve this problem would be to do a big rectangle that is 6 by 8 and then subtract from it a smaller rectangle that I think would be 4 by 6. You can use negative areas. It makes a whole lot of sense when you have like a big rectangle with a circular hole cut out of the middle of it. It's a lot easier to subtract a circle than to add up all of these pieces that are around a circle. All right, let's try another example. Example 2. This one is made up of kind of 3 boards attached to each other so that it ends up looking like that. And we're given that this is the horizontal x-axis right there. And we're given some dimensions. It's broken up into a horizontal rectangle and then 2 vertical ones on the sides. The dimensions are, all of the boards are 2 inches thick. This length down the middle is 12 inches. I mentioned these are both 2 inches thick. And then on the sides, these are actually 6 inches long. They don't really look like it in my picture. So it's 2 inches plus 4 inches for the rectangles on the side, on both sides, exactly the same. 2 inches and then 4 inches. And we're only asked in this problem to find y bar, the vertical coordinate of the centroid. And it's going to have to be down below the x-axis because my x-axis is at the top of the part. And so somewhere down here, I don't know if it's going to be inside of the part or down below it, but somewhere down here is the overall y bar location. Okay, so when I went to solve this, I split it up into 3 rectangles like this. I made this one blue on the right. I made this one in the middle pink. And I made the one on the left green. And I went ahead and made a table. In my table, it doesn't have to be quite as wide since I'm only finding y bar this time. I've got, I guess I need to number my shapes. Call this one 1, the pink one 2, and the blue one 3. So I've got shape number 1, 2, and 3. And then afterwards, I'll have the summations. So I'll do the areas first. Shape 1 looks like a 2 by 6 area. So 2 times 6 is 12 square inches. And shape 3 looks exactly the same. So I'll write it down while I'm at it. 2 times 6 is 12 square inches. And the one in the middle is different. It's 2 times 12, 24 square inches. And if you add those all up, you get 48 square inches. Next, I need to find the y coordinate of the centroid. And I don't honestly mind for a problem like this if you call them all positive distances or negative distances. They are below the x-axis, so you can call them negative distances if you want, or you could define down as positive and call them positive. I'm going to call them negative because they're below the x-axis. So that first rectangle is 6 inches tall. So halfway down would be 3 inches below the x-axis. So I'm going to call this a minus 3 inches. The blue rectangle is also minus 3 inches. And then the pink rectangle is only 2 inches tall, and it is sitting right on that x-axis. So I just need to come down 1 inch, call that a minus 1 inch. So if I multiply those together, I get all my y tildes times areas as minus 36 inches cubed, minus 24 inches cubed, and minus 36 inches cubed. And when I add those all up, I get a minus 96 inches cubed. To find y bar, I take the sum of the y tildes times area divided by the sum of the areas, which is minus 96 inches cubed divided by 48 inches squared. And this comes out to be exactly minus 2 inches. And hopefully that makes a little bit of sense given the shape. We know that the value has to be in between the minus 1 and the minus 3 because we're taking basically a weighted average of those values, so it can't end up outside of those. And so minus 2 seems to make sense for this problem. And now I've given you 2 examples where the numbers come out perfectly evenly, and they're easy numbers because we're in inches, so they're all small numbers. Let's do one that's a little bit more challenging. This will be our 3rd example for today. Example 3 looks like this. We have a y-axis and an x-axis. And first up, we have a triangle. So that's new. Next to the triangle, we have a rectangle, like so. And then next to that rectangle, we have another rectangle. It's actually quite long, so I'm going to scoot my x out just a little so I have room. There's my 3rd rectangle. And then let's get some dimensions for our shape. This is 30, 30, and then 100. 30 millimeters, 30 millimeters, 100 millimeters. And vertically, this rectangle is 50 millimeters high. Then we go up an additional 40 millimeters to the top of the other rectangle in the triangle. And that should cover everything that we need. Let's shade these in, assign our shapes. So if I do, this one is make this a green triangle, and then maybe a pink rectangle, and finally a blue rectangle. I'm going to label this shape 1, 2, and 3. And I do need to find the centroids of each of those shapes. So this one will be right in the middle of that rectangle. This will be right in the middle of that rectangle, basically where I drew my 3. And for the triangle, you might remember this from distributed loads, but a triangle is always going to be 1/3 of the length away from kind of that right angle. So let's find some of these dimensions before we go too far. The centroid of this blue rectangle will be half of the height. The height's 50 millimeters, so that's going to be a 25 millimeter height. The width is 100, so this location relative to one of its edges is 50 millimeters, but we're going to need to add in an additional 60 millimeters to get that measured all the way back to the y-axis. For the pink rectangle, its total height is 50 plus 40, or 90. So half of that means that this centroid's height is going to be 45 millimeters up. And its distance from either of its sides will be half of its width, or 15 millimeters. So then I'll need to add to it another 30 millimeters to get that referenced all the way back to the y-axis. And then for our triangle, you might remember from distributed loads that 1/3 is the number you want to use for a triangle. Whenever we have a side of a triangle, like this one that's 30 millimeters long, the centroid will be 1/3 of the way over. So instead of 30 millimeters, that distance will be 1/3 of that, which is 10 millimeters from the right edge, or 20 millimeters from the left edge. And then vertically, the whole triangle is 90 millimeters tall. So this guy will be a third of that, 30 millimeters up from that edge. So we found all of those locations. We've got a couple of different strategies that we can use to solve for this problem. One would be to simply take the triangle, green triangle, add to it the pink triangle, and add to it the blue triangle. That will work perfectly fine to solve this problem. Green triangle plus pink rectangle minus blue rectangle. There's one strategy. Another strategy you could use, which would also work, is you could do a giant rectangle that includes all of the area. It would be 160 wide and 90 tall. And then you could subtract from it the missing stuff. So a triangle up here in this corner minus a rectangle up there. So you could take the giant shape and subtract the two holes from it. I'm going to do it with the first approach. And let's first write it out with a table. So on my table, typical table, start with a line. We're going to have the different shapes, 1, 2, and 3. Followed by a place to sum them up. And so let's first find the area of each shape. Shape number 1 was a triangle. And so that's the formula for the area of a triangle is 1/2 base times height. The base is 30. The height will be 90. I get that from the 50 plus 40. So 1/2 times 30 times 90. And those are both millimeters, so we'll be in millimeters squared. Next is the pink rectangle. It appears to be 30 by 90. So this one's just 30 by 90. And then the last one is the blue rectangle, and it's 100 times 50. And if you multiply those all out and add them up, the total area comes out to be 9,050 millimeters squared. Okay, next we need to find X and Y locations of centroids. So shall we do X tilde first? So we're finding X coordinates of centroid. Oh, this is actually the harder one. So for that first triangle, we know that the centroid X coordinate is 10 millimeters from the right edge. The whole thing is 30 millimeters wide. So I actually want to use 20 as my distance to locate that centroid from the Y axis. So I got 20 millimeters right here. For the next one, that's this rectangle. The width is 30, so the centroid is 15 millimeters over, and then I need to add to it this other 30 millimeter gap. So 30 plus 15, this one comes out to be 45 millimeters from the edge. And finally, the big blue rectangle, its centroid is 50 millimeters from its left edge, and then I need to add to it 30 and another 30. So 50 plus 60 is 110. I don't need to add those up yet. What I would then do is multiply the X tildes times the area. Those come out to be 27,000, 121,500. And this third one comes out to be 550,000. These are all big because we're talking millimeters. We had millimeters squared times another millimeter, so there's a millimeter cubed. When we add these all up, we get 698,500 millimeters cubed. And so right now we can go and solve for X bar. X bar is the sum of the X tildes times area divided by the total area. So it's 698,500 millimeters cubed divided by 9,050 millimeters squared. And the answer comes out to be 77.2 millimeters. And we can right now do a quick sanity check on this one. The whole shape was 100 plus 60, 160 millimeters wide. And we just got an answer that was 77, which I find encouraging because that's in between 0 and 160. And anywhere you might have made a mistake here, if you get something bigger than 160 or smaller than 0, you know you've made a mistake. We can actually do a little better than that. If you look at all of your X coordinates, 20, 45, and 110, we know that our centroid location has to be in between those. It can't be any smaller than 20 or any bigger than 110. And this seems to pass that sanity check to me. Let's do the y direction next. We need y coordinates of the centroids. These are actually a little easier to find because all of these shapes sit right on the x-axis. So for the first triangle, it'll be 30 millimeters. Then for the rectangle, 45. And for the last rectangle, 25. So my y tildes are 30, 45, and 25. And when I multiply those times the area, I get 40,500, 121,500, and 125,000. So I sum those up and I get 287,000 millimeters cubed. So to find y bar, we just drop that number, sum of the y tildes times area over sum of the areas. We get 287,000 millimeters cubed divided by 9050 millimeters squared. And the answer comes out to be 31.7 millimeters. Again, I want to make sure that it is in between my lowest 25 and my biggest 45, and it is. And 31 seems to make sense given this picture. Most of the area is down closer to the x-axis. So even though the shape gets as high as 90 millimeters, we're expecting our centroid to be somewhere down here where most of the mass is. If you wanted to do this with the inline approach, you are totally welcome to do that. Let me just write it out for one of these. X bar equals, I need a great big division sign. And what I'm going to do is first write down each of the areas. I got 1/2 times 30 times 90. On the top, I'll also have 1/2 times 30 times 90. And then I need to figure out how far over is the x coordinate of that centroid. And we found that already. It's this 20 millimeters over from the axis. So this gets times by 20 millimeters. Repeat for my other two shapes. For the pink rectangle in the middle, my area was 30 times 90. So on the bottom, I'll have 30 times 90. On the top, I'll have 30 times 90 times something else. And that's the x coordinate of the centroid, which we figured out was 30 millimeters plus 15 more, or 45 millimeters. And then finally, for our last rectangle, that one was 100 times 50 for the area. And its centroid location was, we had to start with 30, plus 30 is 60, plus 50 more, 110. And we drop in a 110. And if you do all of that multiplication correctly, you will get this same exact 72.2 millimeters that we found before. I would not do both. I would not write out the table and then write it out this way. The idea with the table is you're doing each of these calculations one by one and writing them down as you go, which I do think for most students is good for going back and finding your mistakes later if you do have mistakes. Once you get good at this and practiced at it, probably directly writing it down is a little bit faster. That concludes today's lesson on finding the centroid of a built-up shape. We're going to use this again next week when we move into the next chapter and learn about area moment of inertia. So you'll get some good practice on this week's homework, and then you're going to get to practice it again next week with when we add another topic onto it.